the same outfit as on the picture. So I swear I have other outfits. Good. There'll be an interactive bit in a bit. I think if you want to volunteer, I need some help. Right, so yeah, as I mentioned, so I work on mostly computer simulations, simulating the universe in its evolution on different scales, which means I don't go to telescopes. I don't have that fun part of the astronomy job. But I go to computer places, or I log into computers that are in different places, rather, and then we have some fun time trying to reproduce in the in the computer what we see in the data and try to explain what we see. So I wanted today to give you some motivation for why we spend a lot of time doing computing stuff, and showing you some example of the things we have done. Let's see if this works. Okay, so just go back to the very basics. So, when we do science, there's a so-called scientific method where we try to test different theories. So someone will try to write down a theory, a model of some kind for a phenomenon they think about. Particle physics or like chemistry or something. And then the idea is that someone else will perform an experiment and will go back and tell the first person whether they were right or wrong, whether their theory matches what the experiment says. So if there's a lot of smoke or like green and orange liquid and that's not part of the equations, then maybe something was wrong with the equation and we have to rethink the theory in the first place. Right? And so there's a back and forth dialogue there. And then so the idea is that to do experiments to usually demonstrate that the theory is wrong and see whether you can then find some improvements. Now the problem with astronomy is that we can't really do experiments. So I can't go to a lab, I can't go make an experiment where I construct a star, I can't construct a planet, I can't even less so construct a galaxy. And the other problem you have is that things are moving very, very, very slowly. So you can see images, you can build a very nice telescope, but I can't go back and change the parameters in my experiment. I can only see what is there. I can't go and move a star somewhere and see whether that changes the evolution and to test the theory. So I only have static pictures, and I don't have any link necessarily between them. And so you have observatories. You can go to your favorite observatory in the center of town on one of the rare blue sky day and try to do some observations. But again, this is only going to give you some static images of things. And we heard before people are going to observe this star to see if this clump moves over 3 years. We're looking at a nearby star. You can do this. If you do the spherics experiment we heard at the very start in the news, nothing will move over the time scale of this thing. We will not see. We will just see the same points. Nothing is going to change. So we don't have any real sense of the evolution of what is happening. Okay, so what do we do? So in practice, our job is to say, well, okay, we cannot try to have the simulations to the rescue, right? So what we're going to do is that I'm going to take the equations or the theory that someone proposes, and we're going to hear the next talk about possible theories of gravity, for instance. And then my job is that I'm going to teach a computer, here my Lego computer, how to solve some of these equations. And then I'm going to use my computer to make predictions. So for instance, here I teach my computer all of these equations for atomic physics and gravity and everything. And out comes a series of galaxies. And then someone buys me or buys us a big telescope, like for instance the Euclid mission here, which is a big European project, goes out and observes thousands of galaxies, millions of galaxies, and then we check whether these match. And then if they match, well, we're happy. If they don't match, then we have to go back and either change the theory or find the bugs in my computer program, or probably a bit of both, until we find something that we're happy with. The advantage here is that because we have a computer, we can change all of the equations as we go, and we can simulate. The other problem is that actually complete solutions where we can compute everything is very, very hard. So if you've been in the center of town, you'll have seen that the physics department has decided that Einstein's equations were famous enough that they deserve to be on the Boerhaave Museum. And so this is a nice form that we like to teach. This is what Einstein's theory of gravity looks like. So it's a bunch of a few symbols, looks nice and tidy. But if you start expanding this is actually what these symbols represent. Right? And then it gets very dirty. And then if I just expand only this first bit here, this is what this looks like, and then you have the rest for all of the other things. Right? So now if you ask the question, can I sit down and write a pen and paper and try to solve this equation for anything interesting? It's nearly impossible. And actually, no solutions to this set of equations for empty universe or for a universe with just one black hole. And then everything else is very, 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 very difficult. But we can try to teach computers how to solve some of these and then make progress rather than relying on our pen and paper and blackboard activities. And it's so hard actually that you can take the simplest problem is just to have 3 stars. So if you have, if you take, say, a star and a planet, we know how to solve this exactly. But if you take 2 stars and planets, or 3 stars or something, just orbiting together, this problem with just 3 planets, 3 orbits, 3 bodies, it's called a 3-body problem, doesn't have a solution that you can write down. So you cannot solve the equation from Newton, you cannot solve the Einstein equation, or any other description of gravity to complete the evolution. So you actually, even at that stage, need computers, even for the simplest problem. Okay, the simplest would probably be 2, just a star and a planet, but if you just add an extra thing, it becomes too hard. Okay, so then the problem is, how do I teach these horrible equations to a computer? So that's part of the game. And so if you have done, if you remember your high school physics, a lot of the physics is often described in terms of differential equations, or maybe derivatives, or integrals, and things like that, which are things typically computers don't even know how to solve either. So what we'll have to do is that we'll have algorithms that will try to approximate the solution to an equation. So, I said we cannot do, already doing 3 planets or 3 stars is very difficult with gravity, but let's just do a few more. So what are we going to do? So if I have a bunch of particles, or planets, or stars, or whatever you want them to be, or asteroids, what we're going to do is that we're going to just do very much like a movie, right? We're going to do just step by step, very slowly, with very slow jump in between, right? Remember if you think about movies, just different frames, and if they go fast enough, we see the motion, we're going to do exactly the same thing. So what we're going to do is that we're going to take all of these planets, say, we're going to compute all of the forces, and we're going to come back to this in a minute. So we're going to compute all of the forces, all of the interaction between these planets. Then if we know the force, we probably remember from high school that the force is equal to the mass times the acceleration. So that tells us how we can calculate the acceleration of every one of these planets. And then what we do is that we say, okay, so if I know the acceleration right now, well, that tells me what the velocity is going to be. So I can calculate the velocity just a tiny bit further in time, and then do very small jump in time, right? If I look at the position of planets, and I add the current velocity, and I say, okay, I move the velocity for like 1 minute or 1 second further in time, they're just going to be at almost the same position, and I can repeat the process. And if I do this with small enough jump in time, I can reproduce the whole trajectory of every one of my particles, of my planets, very precisely. Right? So we decompose the problem by having very tiny jump in time, and every step we go back to the start. And now this is very, very tedious. It takes a lot of time. If you're going to do this with just this set of particles here by pen and paper or on a blackboard, it's going to take forever. But computers are very, very fast. They compute a lot of math operations very quickly. So that's where we came. So this is a very, very painful thing to do by hand, but it's actually very quick to do on a computer. Now the tricky part is how to compute all of the forces. Right? There are many algorithms that exist to do this. And I thought we were going to try something today, where we're going to try a human-based version of this. So we're going to try to process what we call a relaxation algorithm. So I need 7 people to volunteer. Please. There's not going to be any, nothing dangerous. Come on. Come on. Okay, I need you to be on the line. That's not 7 yet. Right? Another one. Good. Can you move forward a tiny bit? Everyone? Good. We're almost 7. That's okay. Okay. So the 2 people at the edge, you don't move. You just serve as, you're the edge of the universe. Okay? The 4 people in the middle, you can move forward or backwards by as much as you like. Well, don't fall. Good. Okay, so that is now our starting point, right? So the straight line we had at the start is the solution, right? I want a computer to find, so this is an empty universe, so there's nothing, the solution is a straight line. And I want my computer to find a straight line. So what I'm going to ask everyone who is in the middle, again, the 2 people at the edge are the edge of the universe, you don't move. Thank you for your service. Everybody else, so the 4 people in the middle, I want you to look at your neighbor on the left and your neighbor on the right. Good. And you judge approximately where the middle point between those 2 people are. No, don't move yet. Okay, have you done that? Okay, now I want you to move to that point altogether. The edge of the universe doesn't move. Okay, now repeat the same step. So the 4 people in the middle, check the middle point of view on your neighbors. And then we move again to this new position. And then we know the step, same again, identify the middle point. Good, and you move again. And you move, and another step, maybe we need another 1 or 2. And another step. Okay. So we recovered our solution, right? Our solution is an empty universe, we end up in a straight line. I'm going to try a different initial pattern maybe. Okay, middle people move to some other random setup. Good. Are we ready? Okay, go to the middle point. Try again. Next step. Okay, continue. 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 A bit more. Good. And so it's called relaxation because it relaxes slowly to the correct solution. Right? And so we have an algorithm here whereby looking at the left and the right, you are finding the middle point, you're identifying, and then you're slowly converging towards the solution. Okay? Thank you for your service. So for those, so you know this sounds. So what we're trying to solve is this is a very easy solution because we just had an empty universe with no constraints, so everybody's just on a straight line. Now the algorithm itself here sounds, we're doing this like by just moving people. In practice, it's called a Gauss-Seidel relaxation algorithm with red-black ordering and Dirichlet boundary conditions. So this is exactly what we would do on a computer. Normally, we will not do this with 7 people. We'll probably do this on a grid in 3 dimensions with maybe 1,000 people on each direction. So maybe with 1 billion people, we could reproduce a real calculation. And then the difference is that the solution would not be a straight line, right? So how can we do this? Well, if we had more space, one thing we could do is that we could do the same exercise on these stairs. Right? So when going up the stairs is harder than going down, so instead of taking the midpoint, you would go slightly up or slightly or more down. Right? So that's essentially saying if there's a constraint in the background, so a constraint from the stairs, we could find a different solution. So for instance, if we could imagine that the stairs represent, it's like representing there's a black hole at the bottom, it's more easy to go towards the black hole than away. So they would actually give us, at the end solution, instead of having a straight line, we would end up people having a V shape like that. So that we find a solution where instead of being an empty universe, we have a more complicated setup. You could also attach people with like elastic bands to the wall and have the same problem, but I think health and safety will not let me do this. And so, in 1 dimension, this would be like the potential created by a black hole. So the same thing applies, and I do this on a computer by trying to find the left and the right for, then in 3 dimensions, you also have to care about front and bottom and up and down, but it's exactly the same algorithm. And the reason it works very quickly is because computers are very fast. Okay, so now that I know who to calculate my forces, I can look at just some examples. So this is one of the oldest examples. I think it's as far as I know, it's the oldest example of a movie of a simulation. Play that. So this is from 1960. So, and actually at the time, so they're going to show you how. So this is just starting from a round distribution of stars. It's not many stars because the computing powers are very, very limited. But they wanted to show how spiral arms in a galaxy can form. So the fun part about this example is that so they presented this at a conference in Princeton, but before that they presented it at a conference in Leiden. And at the time was way before conferences had projectors for movies, or even before they even had projector for slides. And so what they had to do is that they actually took everybody, at the time the physics department was at Kamerling Owners building downtown, but they took everybody to the cinema. The whole conference had to go on a day trip to the cinema to look at the movie. That was probably a very exceptional thing because nobody else, now every day, every time I give a talk I show movies, but at the time it was a really exceptional thing. We all had to go somewhere and look at it. And so this was just to demonstrate, I didn't follow through, but you can see how spiral arms can form. And what was happening is that there was a slight perturbation. It wasn't perfectly circular at the start, and that created a pattern. Right? And so this is 1960. So there was 100 elements in this simulation. Now we can do simulation with tens of trillions. So 1 followed by 12 zeros, and this is 1 followed by 2 zeros. The computing power has increased exponentially. So this is what we can do nowadays. So this is from our recent project with also these 2 people here that were doing boundary conditions before. So this is now simulating some galaxies interacting. There's a bit of sound when we form more stars. So now we can simulate the whole evolution of galaxies, how they collide together, how they're going to have black hole activity. So the idea is that we, in this kind of model, we put in all the ingredients which think are necessary. So we have the laws of gravity from Einstein, we have the laws of gas physics, we have a bit of atomic physics to tell us how the different elements interact. There's a bit of understanding of the black hole physics, and we put this all in a computer, wait for months or 2, and then ideally someone else would come and tell us whether the resulting images or the resulting galaxy patterns or the bars or everything we can see resemble the real data. And if not, we go back and try to figure out what we are missing in our model, or are the important ingredients in our modeling which are missing. The other thing which is interesting for looking at these movies is that it's really, this is over the whole simulation time is about the age of the universe. You can see how very disturbed everything is. So I said before, everything is very quiet. When you look at galaxies, everything looks very static and still. But actually, if you look for long enough, which we obviously can't do with real observations, a lot of activity, everything is rotating, everything is moving, things are colliding. There's stuff happening everywhere. Okay, so what I'm specifically more interested in, and why I'm typically doing simulations, is to understand how our universe works. And so, as I said before, what we do is that we can put our base ingredients, and so we know the starting points, and I think we're going to hear a bit more about this in the next talk. We heard about, for instance, like spherics, we heard at the very start today in the news, is measuring the position of all of the galaxies. So we know the starting point, we know the end, and we have all kinds of people who come with theories about how the universe works. We know we need some amount of dark matter, but what is dark matter? We don't really know. We can have different ideas from particle physicists about what dark matter could be. Maybe we need to change the laws of gravity. Maybe Einstein was not correct, and there may be some tiny differences, or maybe we need to add extra components, right? And so what do we do? Well, as I said before, I try to take some of these models, plug them into the computer, and then see whether the resulting, whether the resulting patterns look like the real data. And then we compare this again to the satellites. So here's just, again, the large-scale evolution, so maybe more closer to what I'm interested in. So here we are looking at the larger section of the universe. And what we see is at the start it was all very, very uniform, because the universe was very, and then the universe expands, and then gravity plays its roles and form all of these filaments, so we call all these non-structured filaments. This is the cosmic web altogether, and in the center of all of this, can maybe play once more. At the center where the filaments cross, these are called halos, and at the very center are the galaxies. So the galaxy we saw before in the movie would be at the center of one of these, where filaments meet. This is where galaxies here form. Right? And we, in our Milky Way, we would live in one of these relatively unremarkable spots in one of these filaments. So if I want to change the laws of physics, what we're looking for is patterns in the sky. And so here are, for example, examples where I simulate the same starting point, but I change the nature of what dark matter is. So I can say, oh, I think dark matter particle has different properties. And then I can see that the filamentary structure is slightly different. And so now I can make predictions for these different theories. And then hopefully someone can go and do measurements of how fluffy the universe actually is. And you can see a range of fluffiness here. It's a very technical term. And then different, so this would be something like a cold dark matter particle, and then you would have some different particles here all the way going to, just different theories of what the dark matter, unknown dark matter particle could be. But then if people can tell me the universe looks very clumpy or more smooth, then we can sort of rule in or rule out some of the theories. But this can only be done by the simulations, because this is too complicated, as I said before, to compute by hand. So just to finish off, just wanted to show you what these computers look like. So they don't look like a laptop or even a desktop. So this is currently the biggest computer in the world. So this is called El Capitan. It's in Lawrence Livermore in the US. And so you have, I mean, looks like wardrobes. In each of these you have about maybe 20 or 30 drawers in here. We shift on them a lot of CPUs, and you have wardrobe after wardrobe after wardrobe, and you have many rows of these. The one in the Netherlands is called Snellius. It's located in Amsterdam on the Science Park. Same thing, just smaller scale with a different painting on the box. And it's run by SURF, which is the Dutch computing center. And then people like to quote the capacity of this computer, so they use this unit which is called a flop, which is not very great. But it's a floating operation. It means it's a multiplication you can do in 1 second. And so this computer can do 14 petaflop, which means you can do this many calculations per second if you use the computer very efficiently. Now this is a very big number. As you know, basically impossible to represent what that actually means. In practice, this is closer to something like 16,000 high-capacity computers. So if they connected together in the same room, so they can really talk to each other very quickly. So if you're taking 16,000 very high-end desktop machines, put them all together in a big room, a lot of cooling, a lot of ventilation, and a lot of noise, you can get your own supercomputer. And then I can come and play with it. Right, and so to finish off, I'm going to stay here. This is what I do. We do all kinds of simulation on different scales. The problem is the same in astronomy. Everything is, we only have, apart from what is in the solar system, almost nothing moves. So we like to simulate things to see how things evolve, to make predictions for different theories. We can simulate planets colliding, we can simulate galaxies, we can simulate whole sections of universe, or the activity of jets, or around black holes, all kinds of different things. And this is all a very exciting topic, and it's fun if you don't want to go to telescope and work at night, but you prefer staying in your office and play with big computers. Thank you.
Okay, so thank you, Matthieu. We now have some time for questions. See hands for questions. Yes, I think I go first.
Yes, I'm not a physicist, so forgive me if it's a stupid question. But you explained that you can do experiments, so you use simulations, you have a set of equations, and you match your simulation with pictures of telescopes.
Yep.
So are you worried that you at some point get the perfect picture, but maybe still your equations are wrong because another set of equations could also make that picture?
Yeah, I'm also not a physicist, so that's fine.
Very good.
Yes, I mean that's always alright. So you could have, even without the simulation, right? You could have two different theories that predict the same experiment result, and then you still don't know which one is the correct one. So then what you could do, well, you can try to think about another experiment you could do that would be able to distinguish between these different models. The simulation aspect doesn't necessarily make this more complicated. Only difference is that because you're doing simulation, you have to make sure that by teaching the computer how to solve the equations, you are not making approximations which are incorrect. So you're adding an extra layer of complexity. because the computers don't solve exactly the equation. You do something approximate. If this is the key part that makes your theory match the data, then you have a problem. But hopefully that's not the case. Or you can do. There are also different ways you can solve the equations on a computer. So if you find the same theory, I can write different computer programs that do the same problem in a different way. And if they will match, then maybe I know it's not because my approximation was incorrect, but because there's something fundamental about the theory aspect, hopefully.
What programming language do you use for language?
What programming language do we use for this? So it depends a bit. So a lot of the analysis we do is in Python, for instance, because this is very simple and it helps to very quickly do a lot of the analysis, and it's a very popular language in science in general, but especially in astronomy. For the big computers, typically we will use, because they are very big machines that use a lot of electricity, and then the electricity bill can be quite high. You want to be very efficient. You want to be using something where you're making good use of the machine. And so typically they will be using what is called lower level languages. So typically we program in C or in C++, or sometimes in Fortran for very older approximations, or older codes that are still out there. So something like that.
Yes?
Are there any attempts to use quantum computers to do this?
Not yet, because they don't exist. So the question was, are there attempts to use quantum computers? Yeah, I think when there will be some devices that are usable for something, I think there will be interest in exploring whether quantum algorithms can help with some of the problems. My current understanding is that this is not obvious that the problems we try to solve can easily be done better, say, on a computer, but also it's not something that people have thought much about so far. I think it's more of a pragmatic approach. As long as I can't use it, I'm not yet interested in thinking about it.
Could you please clear up a question I got? You said that the images don't change over time.
Yeah.
And yet the light is arriving at us at the speed of light, isn't it? Now, I have this concept that out there's enormous explosions going on.
Yeah.
Like you can see an explosion on the ground. That happens very quickly. Is there some fundamental difference?
No, so you're right. I mean, I was a bit too simplistic there. So what we don't really, so if you're looking at the planets in the solar system, of course we see them move, right? So, because that's very close by. If you're looking at the larger scale of the scale of galaxies, like something like what we have here, they do, our own galaxy does a full rotation in about 200 million years. So if I look at another galaxy, it's going to be about the same. So we don't see any of that move whatsoever. But you're right that sometimes stars explode, and when a star explodes, we don't really see motion because it's too far away, but we see an excess of light. And so we will see a very bright spot somewhere appearing that wasn't there the night before. So that the kind of things we can see. Yes, you're right. So these kind of things, I guess, change, but we don't see any motion in the sense of like it's a different place in the sky.
Sure, but the light is coming towards us.
Yeah.
Is not the change that we are looking down
Yeah.
the axis going to happen very quickly? In which case, so if you take...
Yeah. So if you have a star exploding in this galaxy, one night it won't be there, the next night it will be very bright, and maybe 2 nights later it will be dim again.
Okay, that's as fast as we can see it.
Yes.
Thank you.
Up here.
Yeah.
You mentioned you can simulate about tens of trillion stars, but then this computer had like a petaflop of capacity, right? And that's quite different numbers. So why don't you simulate even more stars, like a peta of them?
Well, okay, so beta is 10 to the 15, and we can do 10 to the 13. Now, so there's a difference between, so there are different things, right? There's the number of math operations you can do every second. The other problem you have is that you need a lot of memory to put this into the computer. And that's actually often the main limitation. Because you need to be able to store in your RAM the memory, all of the information. These days, RAM is very, very, very expensive. And actually, a lot of these computing centers are now mostly not buying. They're getting more powerful in terms of the number of operations they can do, but they're not necessarily having more memory, and which is sometimes a problem because we need to fit the whole problem in the RAM. And yeah, if you have a lot of money, please come and talk to me.
Having hard drives that you dump the information once in a while in there and then could continue calculating?
Yeah. So we do this kind of thing. So you could do this. The problem is that this is 1,000 times slower than the RAM. So then if you did this it would take very, very slow. So we do this for you do backups and then you do backups even on like tapes because this is very robust to everything.
Take 2 more questions. I think there's one there.
Yes, thank you for your talk. I was wondering, for your simulations, do you just use the differential equations or do you also use machine learning methods, techniques?
Yeah, so the question is, do we use also machine learning techniques? So it's a good, very interesting topic. It's a very trendy topic as well. So the idea would be that, So if someone has a theory and then we make images and then we compare it to the data, but I say, I went from the theory to the images using a machine learning black box algorithm, and now your theory is wrong, or your theory is right. I'm not sure that person will be very happy because we don't know what approximation has been made by the machine learning aspect. So what we prefer to do, at least what I prefer to do, is that as long as we have differential equations we can write down, so if we can write down the equation for gravity, or the equation for fluids, or the equation for gas, or atomic physics, I can all write them down. I'd rather have a computer approximation that I can control, solve this part. Maybe there are bits which I don't know the details of. For instance, maybe we don't understand exactly how stars form. There I could maybe use a machine learning algorithm to try different things very quickly. But ideally, we would like to have full control of the full chain going from theory to the data without having sort of a machine learning black box in the middle where we don't necessarily understand all of the way the prediction was made.
Is there one final question? Oh, yes. Yeah.
Do you also do computing on the GPU, or is it all just CPU stuff?
Yeah, so this is also the other part is that the computing centers now use more and more GPUs, which are these graphic processing units, which are very popular. One for Bitcoin mining, and the other part for machine learning, indeed. And for that second reason, for instance, the Snellius computer, the one I showed the other one, the El Capital, they all now mostly made of GPUs. So we have to make use of whatever hardware is provided to us. So yes, we have to make use of some of these graphic cards, which is not always easy.
Okay, thank you again.